we can even think about complex numbers as being rectangular in any sense, that we can graph them. That was all stuff that was like a new idea to us yesterday. And it's still not obvious to you yet, I don't think, why polar form is of any use to us. You might be thinking, wasn't I really just happy with rectangular form? Why do I need to even give any thought to what r and theta might be, right? Besides like as a matter of curiosity. So today I think you'll see why polar form is not just kind of like a fun thing, it's also very powerful. Do we have all these right now? These all look good? 10, 6, 7, 5, or 6. I think that sounds a little better. I see some hands though. Noah first.
So we can just write 6, we don't have to write out the cosine.
Sure. I mean, since in polar form you'll always be writing 10 cosine of 7 pi over 6 plus I sine 7 pi over 6. They'll always be the same angle both places. If you want to shorten the way you write it, that's fine. Though if it masks for you any understanding, then like don't do it, right? Like if you stop remembering what it means, then that means you've gone too far. Yeah.
Oh, would there ever be a case where it's like cosine theta minus I sine theta?
I mean, remember by the results we built up yesterday, we talked about this being like x plus yi as being like the definition of our standard form that we're going to talk about, right?
Y is negative.
Right. So if y happens to be, I mean, if you wanted, you could set it up so it was x minus yi, but then you'd always have two different angles, right? You have to think about it. I mean, you could make it.
Yeah.
I'm just saying, like that's how we set it up. We decided that x and y were going to be. I mean, x could be negative and y could be negative, but then, which is fine. Like that's what happens here. If you want to consider, so what I'm saying is, if you have like 2 plus, if instead you wanted to think about this as being like 2 minus 2i, and you wanted to like consider this to be x and this to be y, that would be fine. But then you'll not get the same angle as we get, right? And then you have a minus. So yeah, I mean, you can make that work.
In the polar form, not the rectangular form. Like if there would be a minus.
Yeah, exactly. So that's what I'm saying. Is like if we carried this through, what angle has a so the r value here would still be 2 root 2. What angle has a cosine? And then we have positive 2 and positive 2. So what angle is that?
Wait.
Yeah, pi over 4, right? So can we? Is that the same thing as what we just said? Actually? Well, look at it. You tell me.
I mean, it's different angle.
True, true. But if you multiply this out, what is cosine of pi over 4?
Root 2.
Okay, so does that give you a 2? If you multiply by 2 root 2? And what about this guy? Sine of pi over 4 is?
Okay, yeah.
And then so actually this is equivalent, and this is fine. It's just we traditionally like it to be x plus yi, right?
Yeah. Okay.
Just to, but then is pi over 4 like describing where this is in a meaningful way? It's no longer descriptive of that. Even though algebraically you're right, you could write it this way. Pi over 4 isn't what we maybe want to say though if we're like trying to picture this in a coordinate way, you know. So anyway, all right. So we got to the place where we understand how to do this, but we didn't understand necessarily why this is a powerful thing to do. Any other hang-ups from yesterday? You've had fun with the homework, trying out again, going back and thinking about complex numbers. And this went well for you too. It's you know, recast in a new light, but it's all still just trig, isn't it? Okay, there's not really anything new under the sun. All right, so let's actually think about what we can do in polar form now. Our focus is going to be on doing some various types of arithmetic with complex numbers, like of the kind of problems you've done before, but now doing it in polar form. So we're going to look at 2 complex numbers, and I'd like to think about what it would mean to multiply the 2 complex numbers and divide them. And I'm going to suppose that they're in polar form. Okay. So we have z1 and z2 is what we'll name our 2 complex numbers. And the question is, what would happen if we multiplied them? There you have z1 on the left and z2 on the right. And then work it through, right? Let's just do the algebra and see what happens. You multiply R1 and R2, you get R1, R2. And then what happens when you like multiply these two binomials together? You get a cosine theta 1, cosine theta 2. You get some other stuff, right? You get 4 different things. You multiply that all out. I'll collect terms for you kind of here too. So I multiplied this all out. Do you see that I really do have, I multiplied like cosine theta 1 times cosine theta 2, and I got, that's where this came from. How about like cosine theta 1 times I sine theta 2? Does that appear somewhere? Cosine theta 1 times I sine theta 2.
Yes.
Yeah.
There it is. And where's the I? Oh yeah, I factored it out just for fun. Right? And then why did I highlight in red and highlight in blue? What's red? Right? That's the cosine sum formula. In blue, that's the sine sum formula. Very good. So this is cool. So what does it mean though? Well, it means that if we multiply two complex numbers, what happens if you have two complex numbers that have lengths? Is it okay to say that? I don't know. Magnitudes, R1 and R2. What's the magnitude of their product going to be? It's going to be the magnitude of the two. The new complex number will have a distance away from the origin that's equal to the product of the two distances away from the origin that the two original numbers were, right? So that's interesting. What about the angles? What happens with the angles if you know the angle in standard position of one of your complex numbers and the angle in standard position of your other complex number? Then the angle at which the new product of these two complex numbers lies in the complex plane is equal to what? The sum of the two. That's kind of a cool thing that's happening there. So I have the result in a box down here. I just copied it and pasted it down here. I also have the result that makes sense maybe. You might have guessed even if I didn't say it. That this is the result for division. We're subtracting the angles, right? That kind of makes sense. I don't have like a proof there of that, but I think it's quick enough to do that. I think you should give it a try sometime. See if you can do the proof yourself after seeing my proof that the product works the way it does. Maybe you can prove why doing the division, doing the quotient works nicely too. So this is cool. There's like kind of a nice geometric picture here for us to lay hold of. This idea that like we can, when we multiply complex numbers, we add angles in the complex plane. Whoa. Mind blowing. Okay. We're multiplying things, but we're really adding. We're dividing, but we're really like subtracting. Interesting. You know, that does sound familiar though, too. I don't know. I feel like I've thought about that before. Okay. You feeling good about that?
Yes.
Next goal is to try it out here. I'm going to give you two complex numbers in polar form, and I'd like you to multiply them and draw the picture. All right? Let's see if we can do that. So, yeah, don't labor over this too long. Keep in mind, I'm using a shorthand here, but you understand what those mean, I hope. Polar form. Okay. Like I said, we should just be able to like, write down the answers. Not a lot of work to say here. You want to say it, Sean? What would it be? What, say it one again?
Should be 5 times 5. There are
5 times 7.
Oh, not 5 times 7. Then cosine 50. Okay, cosine 50 degrees plus 20 degrees, 10 times 2 plus I sine.
Good. and 50 plus 20 is also known as 70, yeah. So yeah, you multiply the R values, you add the angles. That's it, yeah, there's nothing more to say about it. That's as easy as it is. And as unimpressive as that might seem, keep in mind how difficult it was to multiply two complex numbers in standard form. Well, it's not terrible, right? So it is a little bit of a pain to multiply two like binomials is basically what you're doing, yes? Right, but here it's pretty easy, right? So let's just draw the picture too. 55 cis 50, let's say that looks like this. I don't know. And in green, 7 cis 20 looks like, I don't know, like that. So here's 20 degrees. And here's our 50 degrees. And we'll draw the product in red or something. At 70 degrees we have, so we're adding the two angles together. Sure, yeah, absolutely. Now this one is, the numbers here, on none of these are the numbers real nice, 50, 20, and 70, or none of those are angles that you know and love, but with the help of the calculator we can do that, sure. I'm not done actually with this slide. I'd like to say a few more things that I think are interesting. Okay, are you ready?
Yeah.
You're gonna blow your mind a little bit here. Okay, so what happens when we multiply a complex number? What happens when we multiply by I? Well, can you give me the polar form for I before we actually ask that question? What is the polar form for I? Right now, it's in rectangular form, it's 0 plus 1I, right? What is it in polar form? Can you do it without any work? It's 1 in the, which direction? It's 1 unit away in the complex. Where is I in the complex plane? Isn't it located at 0, 1? Okay, so it's 1 unit away from the origin. In what direction? Up. Yes, I like that. Pi over 2. Yeah. So 1 cis pi over 2, or 1 cis 90 degrees, if you like. Right. That's its polar form. So what happens when you multiply a number, any complex number you like, by I? What happens to it? Or I guess first let's ask, what doesn't happen to it? What happens to it? What doesn't happen to it? It doesn't get any longer, right? It doesn't get any further away from the origin, right? Because the R value is 1. But what does happen to it? The angle gets bigger, or what would you say? I have another word for that. Greater. You add 90 degrees to it, which corresponds to what kind of transformation?
Oh,
yeah, it's a rotation of that point by 90 degrees around the origin, right? Isn't that what happens to it? I mean, you take the point and you keep it exactly as far away from the origin as it was before, but you add 90 degrees to its argument. So that corresponds to it being rotated 90 degrees counterclockwise in the complex plane, right? So that is to say, if I had like a picture, here are a bunch of complex numbers in the plane, okay? And if I multiplied every single one of them by I, what would I get a picture of? Yeah. And if you want to multiply by something else, you could rotate it by some other angle. If you multiply by 1 cis pi over 6 instead, then it rotates it by only 30 degrees instead of 90 degrees. Okay. Cool. Yes. First things first. That's cool. What happens if you multiply? Where is 1 in the complex plane? Just show me with your hands. Right. It's over here. And then if I multiply 1 by I. Where does that go? Well, here, right? What if I multiply by I again? What does that give me? What happens if I multiply by I again? And by I again? All right, and what if I did like I to the 30th or something like we did yesterday? All right, so you see this happen? Right? It's like clockwork, right? And by that I mean it literally is like clock arithmetic, right? We're kind of repeating values over and over again. And the reason is because anytime you hear that in your head, you're like, we keep repeating values. It should feel like a rotation, really, right? We're just coming around in a circle again. We literally are, in fact, coming around in a circle. So we're blowing your mind. By the way, that reminds me of another thought in my head, too. Back in the day, this idea of rotations might have even been the kind of language you used when you talked about negative numbers for the first time. If I asked you, what's 5? You would have been like, well, it's the thing that's 5, I'm standing like 5 units from the origin. And then if I asked you, well, what's negative 5? Well, that's like me, same thing, but 180 degrees in the opposite direction, right? That's like me rotating 180 degrees around the origin, yeah? But if you can rotate 180 degrees around the origin, why didn't you ask the question about rotating 90 degrees around the origin off the real line, right? And maybe at that time, because you're a baby mathematician, you had no idea what the answer was to that question, but you're like, I would like to rotate something other than 180 degrees. So I'm going to rotate by I'm going to multiply by something. I know how to rotate 180 degrees, you said to yourself, baby mathematician that you were.
Yes.
All I have to do is multiply by -1. What do I multiply by to rotate 90, you said to yourself. And then you said, I don't know, self, so I'll call it A, because, I don't know, but I do know, whatever, it's an unknown, because my name's Anna or something. Okay. I don't know what that number is that I multiplied to rotate 90 degrees. I have no idea. But I do know that if I rotate 90 degrees twice, that if I do that, that should be the equivalent of me multiplying by -1. And then I reasoned myself as a baby mathematician that this value I multiplied must be the square root of -1, right?
Oh, and that's I.
And that's exactly what we just discussed a second ago. Rotation by 90 degrees is, in fact, yes, you multiplying by I. Okay, so I know you've never thought about I in that way, but you know what it is? It's the rotator. That's what it is, right? I is the thing that rotates us by 90 degrees by multiplying by it. All right. Go ahead and do these problems. I'll call someone up to do them in a second, each one. Am I changing lives?
I already knew it in elementary school.
No, sorry, you already.
That's the first time I've been told the whole semester.
Well,
It makes you wonder what, wait, is this like in the realm of discrete mathematics?
Well, that's not the right dichotomy. Are you
Like, I'm not sure.
you mean pure versus
Yeah,
versus
I'm not sure if it's applied.
applied?
It's applied just like high stuff.
Yeah. Pure just means we're doing it for the love of the game. And we have no idea what it's good for.
I think I think
So both are reasonable questions. You have two questions maybe. One, is this applicable to the real world? Is that your question? Which is a good question. And then the other question would be like, is there something discrete happening here rather than continuous would be the other idea? Right? Like it seems like there's like some number theory or something involved.
that I mean show math.
I mean, definitely this idea of
That's Z.
we were just discussing about hitting the same point over and over again. There might be something there.
oh, you have the angle of pi.
Number torch.
Oh, it's 2 pi over 3.
Is it possible because like you have like the Argon plane, right? Is it possible that you can add a third plane?
Not and have an arithmetic that's of this kind of form. You have to jump up to higher dimensions. Once you get to dimension 4, you have something equivalent to the complex numbers. They're called points.
Dude, I thought you just
And there's also an equivalent in dimension 8.
It's in its standard form. It's in polar form.
How many dimensions?
Oh, lots of them. But I'm just saying, I think it's supposed to be proven that there's maybe only available arithmetic is 1, 2, or 8. This kind of.
Wait, is this calculator?
That's what I was laughing at. You know, calculator silly. I made that and I was really excited about it.
All right, Justin's coming up to do the second one here. You'll see. It'll be great. Do you know what it's being asked of you? We're just doing, can you multiply z times z? Can you do z times z, please? And then once you get your result, can you please divide by w?
Oh, wait, you asked to get it automatically turn it.
I mean, I gave it to you in polar form, and I told you to write your answer in polar form, so you don't have
But I'm
to.
pi over 3 and
Why not?
Why do you get -6? Why don't you just get 6?
Wait, did I just get really stupid?
Nope. I think you got
So,
it.
I'm probably
Oh, are they calling you unfortunate?
I like totally just ignore everything we just
Yeah.
learned.
All right, hey guys. So Justin's gonna come up and do the second one in a second, but just so we have a discussion about this first one, this is nice. Again, if I took two complex numbers in standard form, this would be a little bit non-trivial. But doing it in polar form is like a yawn fest. It's like, yeah, 6 and pi, done, right? And by the way, do you need to go through the process of converting this from polar form to rectangular form using all those formulas? Well, maybe not, right? Because it's like, hello, we're 6 units away in the pi direction. That's a description of -6 in my mind, right? So, yeah, you could maybe even just like do all that in your head if you wanted. Yeah. Justin, how's that going?
Okay, so I know you get to the, so you get 225 cis 150 over 5 cis 100, so you end up getting like 45 cis of 50.
Sounds good to me.
Is that all you read?
Yeah, put it up there. Write it. Yeah, do you understand what's going on in the second one there? Okay. Yeah, it says do it in polar form here, and then the reason is because, again, if we wanted it in rectangular form, we'd have to reach for our calculator. I just didn't want to.
Okay.
All right, the next challenge is this z squared, you guys, makes me think of something. It makes me think about the fact that, like, yesterday I made you do some things cubed or whatever. Let's consider like what it would mean to take something to like the 7th power. If it's a complex number in standard form, that would mean multiplying 7 binomials and having this pretty terrible product. If it's in polar form, though, can you tell me how that would go? If you're trying to raise a number, a complex number in polar form to the 7th power, how would that feel? You just did z squared. What would you get? What would happen to r? You just get r to the 7th, right? And what would happen to the theta value? It's the same. It's the same theta value, so you just have 7 copies of it, right? Okay, so the next result follows immediately from our discussion that we just had. Is that okay with Justin's work? So he first squared the numerator, z squared, right? It's 15 times 15, and cis 75 plus 75, and then he divides using division. We're doing 225 divided by 5 is 45, and 150 minus 100. Okay, so this follows we just had this conversation verbally, but this follows immediately from the previous result. It's called Demos's theorem, and it just says, hey, if you want to take a number and raise it to a power, a complex number, and it's in polar form, then of course you just get the r value to the n, and you get n copies of theta. It's like, yay, makes complete sense. But you can already see why I'm talking about the fact that this is very powerful. You can see this will save us a lot of time and energy if it's in polar form. By the way, this seems to be a pretty kind of a nice extension of the discrete case where we had just 2 of them. Right? We just had 2 numbers we were multiplying together. What happens if we're multiplying 3 numbers together, or 4, or 5, or 6, or 7, like I said? That makes me think of maybe a way I could prove this result more rigorously. Like for all n. Like for all integer n. Right, so think about how you might prove that statement, Demos's theorem. So we're all the French guys, aren't we, on this unit? Demos. You like French guys? His first name was, what do you think?
No.
It was probably like I don't know, Renee, yeah, or like Jacques or Francois. I like that. Yeah, yeah. Actually, I know his first name. You'll be surprised. His first name was Abraham. Good French name there. All right. Go ahead. Let's raise this complex number to the 5th power. Stop Snapchatting shit though. Okay. So we're just. I could have asked you this. Question on the last slide too, right? Before we ever gave you formally Demaz, you could have just been like, okay, yeah, it's 2 cis pi over 6 times 2 cis pi over 6, etc. All the way down the line. So we get. What do we get? 2 to the 5th.
32.
Cis 5 pi over 6, which is equal to 32, I hear someone saying. And cosine of, we have cosine of 5 pi over 6, just to remind yourselves about what this means, plus I sine 5 pi over 6. What is the cosine of 5 pi over 6? Good job. Sine of 5 pi over 6? Okay, so here we go. In rectangular, it says it wants it in rectangular form, so we'll give it to him. Negative 16 root 3 plus 16i. Notice, guys, that that's nice, and that was quick. So nice. Taking a polar form of a complex number and raising it to the 5th power is so nice that even if someone gave it to me in rectangular form in these parentheses, I might go to the trouble and ask, both gave it to me in rectangular form and asked for the final answer in rectangular form. I might still, even though it was never mentioned in the question, I might still go to the trouble of converting it to polar form, doing my work, and then converting it back, right? Because this is so quick and easy. Which is exactly what I think you should do here, too. You good? All right, so we're going to take this guy to the 4th power. Notice that the question is given in rectangular form. And the answer is that we desire the answer to be in rectangular form too. So let's see how we do here. Okay. So my suggestion to you is that we put this in polar form because that was so fun to raise something in polar form to the 4th power. Now I give you one that I think you can just do in your head. Am I right? What's the R value? How far away are we? The R value.
Oh, not 5 pi over 4.
Isn't it 1? Do you see why? I mean, I gave you numbers that should be familiar to you. Isn't that a point on the unit circle? Right? So, of course, by on the unit circle, we mean 1 unit away from the origin. So, yeah, this is just 1 cis, what'd you say, Maddie? 5 pi over 4?
It's 3 pi over 4.
I think 3 pi over 4. Tough crowd? Yeah. All right. So now you see how that was a nice move. So rewrite it that way. Because now the answer is.
You had 3 pi over 4.
So it's just cis.
Wait, what's that?
3 pi. So what is this? This is a number that is 1 unit away from the origin in the 3 pi direction. So what is that?
Pi direction.
AKA the pi direction. So what number are we talking about? 1 unit away in the complex plane from the origin in the pi direction. What number is it?
Pi.
-1. You could actually write it out, right? You could say cosine of 3 pi plus I times the sine of 3 pi, and you'll work it out, you'll get 1. But -1. Okay? Nice problem, isn't it? Okay. All right, are you ready to learn an amazing fact as we close out this period here? We've got 1 slide left, okay? Listen. I really need a lot of sobriety as we just look at this slide. This is going to be mind-blowing, and I want you to soberness. I want to make sure you take this beautiful fact and don't just kind of flippantly pack up your bag. This is going to change your life. This is amazing. It says amazing fact, and it will be an amazing fact. Okay. So we've been dealing with this. We've been dealing with this expression this period. It's the polar form for the complex number z. And this equals, are you ready?
Yes.
But are you really? Are you like emotionally prepared? Are you sitting down? Okay. It equals RE to the I theta.
Wait.
So this result is called Euler's equation.
So cosine theta plus
And
cosine theta.
actually the R is a little bit of a distraction. Maybe I just want to write it this way. E to the I theta equals cosine theta plus I sine theta, right? Okay, just to eliminate the R on both sides. This is maybe the fundamental thing we want to have in view. This is an incredible result if it's true. The first thing I might ask you to do is just for fun, just in this red expression here, just for fun, let's plug in pi to see what we get. On the right, on the left we get e to the I pi. And on the right we get what? What's the cosine of pi plus I times the sine of pi? -1 plus 0. So just -1, right? Or you could rearrange it if you like. It's often shown this way when people display it just because it's pretty. So this equation you've seen maybe, you know.
Saying that e to the I pi is
Yeah, e to the I pi is equal to -1 is what this says. E to the I pi plus 1 is 0 is another way to nicely write it. The reason sometimes people like to write it this way is because this equation that we just wrote down contains all 5 of like the most important mathematical constants and relates them in one equation. E, I, pi, 1, and 0. Right? Isn't that beautiful? I mean, that's the kind of that should be like near the top of your list when you go to like think about which tattoo you get someday or something, right? This is a beautiful, beautiful result.
If you were majoring in math, like me, you
All of this is you taking my word for it. Do you think you can prove this result?
And I'm sure you
And
I mean, otherwise it would.
yeah, otherwise. Yeah, so think about how you might prove this result. You've already maybe thought about the fact that there might have been a connection between those things. See if you can make that a reality, okay? They seemed familiar last unit. Maybe you can formalize your thought. By the way, remember we said that multiplying complex numbers feels like we're adding theta values? We're multiplying, but we're adding. What does that remind you of? It sounds like exponentiation to me, right? All right, I'll let you go, but you know, more later.